rearranges from least to greatest weight of for structural member to support the 50,000 newtons without experiencing the plastic deformation. And so, I guess the first thing to realize is that you are going to have to use your basically your sigma y equation, or sigma, I guess, which is just force over area. But in this case, we need to rearrange it so that we can solve for the cross-sectional area itself. So actually this is A naught. So if we rearrange this, we'll end up with force over sigma y. So this is what we're going to start with. So now they don't give area, but you have to determine the volume of your specimen because you're trying to figure out the deformation. So to figure out basically how to derive volume from the area or the area equation that's given here. It would basically be described in this way. So it'd be the length multiplied by the cross-sectional area. And then if you write that out, it will look like this. So it's all equal to each other. And they also give us density values as well, so we're not quite done yet. So we know that in order to find density from, or we can find density from the mass equation, well, they're all related, but so you have mass is equal to volume multiplied by density. And so knowing this, we can plug that into, or just say use what we know here and apply it into that equation. And we'll end up with mass is equal to volume times rho, but that is also equal to rho multiplied by the length of that member multiplied by the force divided by that yield stress, or divided by that yield stress. And so from here, at this point, it's just you just plug in your values, and for each of the different members. So I won't plug in because that's the last stuff we have to plug in, but I will show you guys at least the values that you should get for each one. So the first one is the mass of the brass. So basically if we plug in all of our values for brass into this equation up here, you should end up with about 102 grams. So the mass for steel should be about 46 grams. I believe aluminum is on there, but instead of writing out aluminum, I'll just say this. Which is about 43.5 grams. And the mass of the titanium is going to be about 40.9 grams. So as we see from all the values that we wrote down, titanium is going to have the minimum weight or mass, followed by aluminum, steel, and brass. So basically from least to greatest, so this would be 1, 2, 3, and 4. So let's recap on this one a little bit. So we're essentially using our yield strength equation, but we're altering it so that we can isolate that cross-sectional area. And then we're breaking down that cross-sectional area so that we can determine the mass of each of those elements by basically turning that cross-sectional area into a volume. And once you break it down and you understand that, you basically plug that in and just use this mass equation down here. And then from there you'll be all set to plug in values and everything. And this is how you would write them once you plug in your values and solve. Yeah.
Doesn't it just say like 100 meter or 100 millimeter? Well, is that, or are we just assuming that's what it is?
Oh, so yeah, so we wouldn't be needing like instantaneous area. So I mean, we know that our signal y is equal to f over basically a naught. We're not using the a naught. We're basically kind of using that as kind of like basically like a doorway, so that we can break that down into values that we do have. Because the only thing they gave us was yield strength and density, and then to get density, you have to know your mass equation. But once you write down your mass equation, you'll realize that you're missing volume. But you can find volume by multiplying that area by length. And then, so basically, once you do that, you get that third dimension, because we know volume is three-dimensional. So yeah, so the area, like with this kind of question, you can definitely see it be kind of like a smoke screen a little bit, because they give you everything except for the area, which that's kind of neat. But then if you look closer at the problem, you'll see densities there. So then hopefully that should give you an indication that you gotta keep breaking down areas so that you can get to mass. And so you actually use that density value, those density values that they gave. Any other questions on this one? So the next section that they were speaking about was basically the heat treatment of steels. So essentially they mentioned how conventional heat treatment procedures for producing martensitic steels, it usually involves some sort of like rapid continuous cooling of some austenitized specimen in a quenching medium, and that means like water or oil or something here. And you can transform that austenite over a temperature range, as you can see like from here within this spot, into all sorts of different microstructures, and it can have different properties, etc. If you keep reading into the chapter, they mention, I guess the three factors that kind of, I guess to expect or see, or I should say the successful heat treating of steels to produce those martensitic microstructures throughout the cross section is going to depend on like the composition, the type and character of the quenching medium, and the size and shape of the specimen. And then in there they mentioned hardenability and things like that. I don't think we're going to need that for this next question. And this next one is kind of the last one for chapter 11, which kind of looked a little difficult. So the problem reads, is it possible to temper an oil quenched 4140 steel cylinder shaft, 12.5 millimeters in diameter, so as to give a minimum yield strength of 1,000 megapascals and a minimum ductility of 16% elongation? And if it's possible, they want you to specify the tempering temperature. And if it's not possible, then you gotta explain why. So actually, we need to know a little bit. I've noticed with this question, they don't necessarily point you to this table. You kind of just like have to know that you need to go and look at that table, which I don't like that question for that. So in order to solve this, we're going to use this table, but let me make sure I understand correctly. Actually, let me see if I can try and copy and paste. Try to see if I can chop it, make it smaller so that you can see it from up there. Not easy to see. Okay, so the problem's asking if we can temper an oil quench 4140 steel cylinder shaft with a 12.5mm diameter, so as to give a minimum yield strength of 1000 megapascals and a minimum ductility of 16% elongation. And like I was mentioning earlier, you have to go to this figure, which is figure 11.24, and you have to look at figure B and figure C to figure out what's going on. And figure 11.24 B and C respectively are showing the yield strength and ductility versus temperature. So for the 12.5mm diameter line in figure 11.24 B, which is this red one, the tempering temperature is less than about 600 degrees Celsius, are required to give a yield strength of at least 1000 megapascals. So you can see here, if I draw it, so underneath that line, you can see the 12.5mm is giving a yield strength of 1000 megapascals. And so, knowing this from the next figure down, 11.24C, for the 12.5mm diameter line, the tempering temperature is greater than about 550 degrees Celsius, which is, so 550 is here. It's going to give a ductility greater than 16% elongation. So if we find this line again, so 550 here. Right, so tempering temperature greater than 550 is going to give a ductility of 16% elongation. So it is possible to temper this alloy to produce the minimum yield strength and ductility. And the tempering temperature would, based on the graph, would then be between 550 and 600 degrees Celsius. So if we draw this up here, so we're looking at the red line, so this is basically what they're mentioning here. So below that temperature, you're not going to get the elongation that you're looking for, but after that temperature, you can. Any questions on this one? If not, that's the last one that was kind of difficult from your chapter 11 that we wanted to go over with you guys. So I'm gonna hand it off to Mehdi, and he's gonna go over chapter 12 with you guys real quick.